So today we're going to talk about naive Bayes, because that's what we've been talking about in class, and that's what your next homework, which is a programming assignment, is about. So feel free to stop me at any point if you have questions. I'm mostly going to be sort of like going over what we covered in class, hopefully with, hopefully maybe a little slower. So I'm happy to stop and answer your questions. Okay. So naive Bayes is a classifier, right? And the goal of a classifier is usually to learn a model that can predict some label y given usually some set of features which we'll call x, right? Where x is usually a vector. It can be more than one feature, right? And so often in a classifier, the model that we want to learn is the probability of y given x, or the probability of our label given our features. So for example, if we're trying to build a document classifier where we want to determine are these documents about science versus about history, then we want to predict the label, science versus history, given a bunch of features which we extract from the document, right? And so there are different ways to learn this distribution, probability of y given x, but one, which is the approach that naive Bayes takes, is to model both probability of x given y and the probability of y, right? And then use Bayes' rule to calculate probability of y given x from those two things. But in order to sort of specify our model, we have to specify these two distributions, and then from there we can calculate probability of y given x, right? And as we'll see next week, you actually don't always have to directly model the distribution of the features, this probability of x given y. There's some other classifiers that sort of take a different approach and just sort of model probability of y given x directly. But in naive Bayes, we don't model probability of y given x directly. We sort of specify distributions for these two things, and then from there we can calculate probability of y given x. Does anybody have questions about that? Okay, great. So as I said before, x is usually a vector, which means you have multiple features, right? So let's assume we have n features. And let's assume for simplicity that we just have a binary classifier, right? So y can either take on value 0 or 1, two different possible labels. So the probability of y is pretty simple, right? Usually it'll be like a Bernoulli distribution, where the probability that y equals 1 is given by p, and the probability that y equals 0 is given by 1 minus p. But what does the distribution of x given y look like? Well, the problem is that if you have a whole bunch of features, then this can be a pretty complex distribution with a ton of parameters, right? So as we talked about in class, if, let's say each of your features xi is Bernoulli, and you have n features, then in order to specify a probability of x given y, well, let's say x1 through xn, how many parameters do you need? Well, you need specifically 2 times 2 to the n minus 1, right? So this is order of 2 to the n parameters. So how do we get around this? In naive Bayes, we make a simplifying assumption of conditional independence, and that helps us vastly reduce the number of parameters we need to model this probability of x given y distribution. So I'll go over that in more detail, but But basically, once we use the conditional independence assumption, we end up being able to model probability of x given y with only 2 n parameters, which is just order n. So we have a much simpler distribution that we need far fewer parameters in order to specify. Okay, so let's go over a quick example of conditional independence so that you guys sort of get the intuition of why this is a reasonable assumption to make. Let's go over here, actually. Let's do this. Okay, so let's say your label is, let's say you're trying to predict whether it's winter or summer, right? So your label could be, is it winter? Or just, we can write winter versus summer. So this is your y. Okay? And then let's say you have 2 features. So feature 1 is sort of the temperature outside. But we'll sort of discretize that into hot and cold. So, if it's above, 60 degrees, we'll say it's hot, and if it's below 60 degrees, we'll say it's cold. Our second feature, let's say, is whether or not it's sunny outside. Okay? So winter versus summer is y, is your label. Hot versus cold is your first feature, so we'll call this x1. And then sunny versus overcast is your second feature, so we'll call this x2. Okay? And basically, when you're training a classifier, what you're going to be given is a bunch of data. So basically, a bunch of instances with each values for each one of these variables, x1, x2, y, right? And maybe they'll all be like different days throughout the course of a year, right? So and for each day you'll have, was it hot or cold? Was it sunny or overcast? And was it winter or summer? Let's forget about, fall and spring for now. And ultimately what you want to do is be able to predict whether it's winter or summer given a new set of features, right? So if you don't know y, can you train a model that can predict y given x1 and x2? So in naive Bayes, we're going to make this assumption that x1 and x2 are independent given y. Okay? And so you might ask, why does that make sense? So let's think about it for a minute. First, let's think about whether x1 and x2 are marginally independent. So if we don't condition on the season at all, is the temperature outside and whether it's sunny or overcast, are they independent or not? And if you think about it logically for a minute. Not really, because if you think about the general season, you might notice that it tends to be correlated, right? Maybe sunnier days tend to be warmer and colder days tend to be more overcast. But if you think about it a little more carefully, the reason for that might just be that in winter it tends to both be colder and it tends to be more overcast than in summer. So there just happen to be a lot of days in winter that are both colder and overcast. And there happen to be more days in summer that are both warmer and sunnier. But there might not be like a direct, say, causal relationship between those two things, because you could have cold, sunny days in winter and warm, overcast days in summer. It's just that there might not be that many of them just due to the fact that summer tends to be warmer and also tends to be sunnier. Okay, so marginally they might not be independent, but let's say we condition on y. So what does that mean? First, we restrict ourselves to just looking at y equals 0. So let's say that's winter. So we only look at the days with label y equals 0. Now maybe in winter, what we notice is that, yeah, there might be a lot of cold days and there might be a lot of overcast days, but maybe they're no longer correlated, right? And similarly, if you just look at y equals 1, which is summer, you might notice the same thing, that even though there might be a lot of hot days and there might be a lot of sunny days, they're not explicitly correlated. So conditionally independent just means that given you're in one label versus the other, your features are now independent and there's no longer a correlation, right? So your features can still help predict whether it's winter or summer. It's just that they're not correlated, they're not dependent. So that's basically the idea of conditional independence. Questions? Okay. Okay, so now let's sort of talk more mathematically about naive Bayes. Okay, so I said before that we wanted to be able to calculate the probability of y, our label, given x1 through xn, which is our set of features. So how do we do that? So here in this notation, I'm using capital Y to denote our random variable y and lowercase y to denote a specific value assigned to y, right? So if we assume that our label is binary, then little y can be either 0 or 1. And here, again, I'm using the same notation. Okay, so how do we calculate this? Well, first we apply Bayes' rule, which hopefully by now everyone's very familiar with. So this is Bayes' rule. Then, since we don't know right now how to calculate the denominator, we're going to sort of put it into a form that we can calculate. So how do we do that? Well, we can use marginalization followed by the chain rule to write it like this. Where here, when I write a sum over z, it's just a sum, again, over all possible values that y can take on, but I'm just using z to differentiate from y up here. But here z is still either 0 or 1, okay? So here we used the marginalization followed by the chain rule. And now we see that both the numerator and denominator are written in terms of the probability of y, which appears here and here, and the probability of x given y, which are the other two terms, right? It's just that in the denominator we have a sum. Okay, and then next we use our conditional independence assumption, right? Which was that, I guess I'll write on the next board. Which was that our features are conditionally independent given our label, right? And when features are independent, it means that their joint probability can be written as a product of their individual probabilities, right? So, how do we write that? So we introduce a product over all the features, and we just write the probability right? Because the independence definition also holds for conditional independence, it's just that you're conditioning instead of just having a marginal probability, right? And then in the denominator, we do the same thing, except we still have our sum. And this is by our conditional independence assumption. So this is really like the critical, like mathematical step that you need to understand in order to understand naive Bayes. Basically, we're taking the probability of y given x and rewriting it in this form using our conditional independence assumption. And this allows us to sort of parameterize our model using a bunch of different distributions, each over just one feature or over the label itself, right? So we have a probability of x given the label for each, of xi given the label for each xi. So we have n things here, and then we have one more distribution that we have to specify over here, right? And so once we define those distributions, that's it. We've sort of defined our naive Bayes model. Okay? And then the only other thing that you sort of need to understand for naive Bayes is how to predict, is like what the prediction rule is, right? So given a new test example, so if you're doing document classification, it would be a new document. What you do is basically you'll calculate probability of y given x for each value of y, so 0 and 1, and then choose the one that's larger, right? So if you get probability y equals 0 is 0.7 and probability y equals 1 is 0.3, then you'll predict 0. Does that make sense? Okay. Cool. So now let's talk about different types of features you can have in naive Bayes, right? So in class we talked about discrete features and a bit about continuous valued features. So we'll sort of talk about how to specify different models with different types of features and how to estimate the parameters of a model so that you have a fully trained model. Questions so far? Okay. Okay, so let's suppose you have discrete features, which means that your x1 through xn take on, some non-continuous value. So for example, let's suppose they're Bernoulli. So then, so basically what we're going to do is we're going to specify, sort of fully specify a naive Bayes model, which means, as I just said, we need a distribution for each xi given the label, and we need a distribution, a prior distribution for the label itself. So if your features are binary valued, then you might assume that xi given y equals 0 is Bernoulli with some parameter p sub I 0. And then you need a second distribution for xi given y equals 1. So again, we'll assume this is Bernoulli with a different parameter. So how many total parameters do we have here that we need to estimate so far? Anyone? Just shout it out. So how many xi's do we have? N. And we have sort of two different distributions for each xi. One for xi given y equals 0 and one for xi given y equals 1. So we have 2n parameters for these distributions, right? And then in addition to that, we want to specify the distribution of y, which again we'll assume is Bernoulli. And we'll call this parameter pi. So we need to estimate a total of 2n plus 1 parameters, right? So in this case, pi 0 is the probability that xi equals 1 given y equals 0, right? And one thing to note is that you can easily calculate the probability that xi equals 0 given y equals 0 without estimating a different parameter, right? Because that probability is fully specified by this pi, because it's given by 1 minus pi 0. Right? So these two probabilities, the probability that xi equals 1 and xi equals 0 conditioned on a particular value of y, those two are fully determined by one another, right? Because they have to sum to 1. But you need a totally different parameter to specify the probability of xi equals a particular value given y equals 1, right? So for that, you need pi1. And that's why we have these two n parameters.
Wait, say that one more time.
So basically, all I'm saying is that, so pi1 is the probability that xi equals 1 given y equals 1. So all I'm saying is, like, you cannot calculate these two from one another, but you can calculate these two from one another. That's why you need two different parameters for these two things, but only one parameter for these guys. That's all. Just the distinction between whether you're changing, like, the label, x, or what you're conditioning on. That's all. Okay, so we need to estimate these two n plus 1 parameters, right? So how do we do that? Well, basically, all we have to do is use either the maximum likelihood estimate or the maximum a posteriori estimate for each of these p's and for pi. And luckily, we learned how to do that sort of last week in class, right? Calculate the maximum likelihood estimator and map estimator for a Bernoulli variable. So just to write it out again, so let's suppose we want to use the MLE. So what's the MLE for pi0? Well, so we know that the maximum likelihood estimator of a Bernoulli random variable is just like suppose you're just doing coin flips, then the MLE is just like the number of heads divided by the total number of flips, right? So the only difference here is that we're sort of calculating the MLE of a conditional distribution, right? Because this is the distribution of xi given y equals 0. And p is the parameter for that distribution, right? So the only difference is that we're going to sort of restrict ourselves to looking at the examples where y equals 0. So basically, this is ultimately going to be the count of xi equals 1 among cases where y equals 0, right? So we have a bunch of training examples. We look only at the ones where y equals 0. We count the number of times that we see xi equals 1, and that's our numerator. And then we divide by, anyone want to tell me what we divide by? What? So it's the total number of times where y equals, the total number of cases in which y equals 0. So not the complete total, right? Just the total number of cases where y equals 0. And that's because it's sort of this conditional probability. So what's the probability xi equals 1 given y equals 0, intuitively this makes sense, right? Okay. And then for the MLE of pi1, does anyone want to tell me what that would be? Yeah.
Same thing for y equals 1.
Exactly, yeah. So the count of x equals 1 among the y equals 1 cases divided by total number of cases where y equals 1. Okay? And if we were using map estimates instead of maximum likelihood estimates, then we would sort of do the same thing, but we would include those pseudo counts, or I forget, I think Tom calls them like hallucinated examples or whatever, right? So it would sort of be the map estimate, but we'd still restrict ourselves to this y equals 0 case. Okay, and then finally, we need to estimate pi, right? So pi hat is pretty simply just the count of cases where y equals 1 divided by the total number of training examples.
You would say like half 1, or
Say that again?
you would say like if I have 1 or something?
Well, you could, but pi, well, so you wouldn't really say pi hat 1. What is pi? Pi represents the probability that y equals 1, right? I think that's what you're thinking of. So how do you get the probability that y equals 0?
1 minus that.
1 minus pi. Yeah, so you don't need to define like 2 parameters, again, because the probability y equals 1 and probability y equals 0 are directly both determined by pi. So after you calculate an estimate for each of these things, you've estimated your 2 n parameters, right? And then you can, then you sort of have your fully parameterized model, and then you can perform prediction for a new example by plugging those things into the formula that I wrote up there. Questions? Okay. So, now let's suppose that your features are continuous, right? So they're not like binary, they're not even, they can't even take multiple values, they're continuous. Like suppose one of your features was the actual temperature, not like is it hot or cold. Then basically a Bernoulli distribution won't do it, right? Because a Bernoulli distribution only works for binary features. You need a distribution that works for continuous features, right? So let's talk about that. Okay, so in this case, let's use the Gaussian distribution because it's a pretty common distribution. So let's assume that xi given y equals 0 is distributed according to a Gaussian or normal distribution with a particular mean. And let's assume that the variance is fixed. So we just like specify the variance. Like let's say it's 1. But I'll write sigma squared just because you can specify any variance that you want. But we won't worry about sort of estimating that. So we need to specify the same set of distributions. We need xi given y equals 0, xi given y equals 1. We'll assume another Gaussian, but with a different mean. And we'll assume the same variance. And then we need, again, a distribution for y, but since y is still the class label, we can still assume it's Bernoulli just as before, right? Okay, so does this make sense? So again, we have 2 n Gaussian distributions and 1 Bernoulli distribution. So 2n plus 1 different distributions, so we've sort of fully specified our model again. So we specified the same set of distributions for the same set of things, but they're just different distributions. Does that make sense? Okay, so now what parameters do we need to estimate? We have pi again, and now we have all these mu's. So how do we do that? We do the same thing as we did before, right? We want to get the maximum likelihood estimate, or we could use the map estimate, but for a Gaussian instead of for a Bernoulli random variable. So I'll just write out what those are. So here, mu I 0 sort of represents the expected value of, or the, like, yeah, it represents the expected value of xi given y equals 0, right? So the maximum likelihood estimator, I won't write down the math, but I'll sort of write down intuitively what it is. So it's 1 over the count of y equals 0. I guess maybe first I'll write over here the maximum likelihood estimator for a Gaussian where you're not really conditioning on anything, right? It's just the sample mean. So 1 over n, or let's write m, where m is the number of examples, times the sum from j equals 1 to m of xj, right? So this is the sample mean. So you add up all your data points and you divide by the total number of data points that you have. So here, it's the same thing, except just keep in mind we're restricting ourselves to the cases where y equals 0, right? So here, instead of 1 over the total number of examples, we have 1 over the number of examples where y equals 0. And then we sum over all examples j such that y j equals 0, where I'm just going to use this sort of superscript notation to denote the jth example. So we're just going to sum over the examples where the label is 0, and we're going to add up the ith feature of the jth example. Does that make sense? Okay. And then for mu hat I1, we'll do the same thing, but replace y equals 0 with y equals 1, just like we did over there. Does this make sense? Yeah. Just, yeah, sometimes it's conventional to put it in parentheses. Not always. I just did it because, I don't know, it helps. It's just notation. It's just notation that I decided to use, yeah. Yeah. And in this case, I'm using I to represent the feature, which feature it is, and J to represent which training example it is. So, like, I could have done any number of things, right? Like I could do xij, both down here. I don't know. I just decided to do it like this. Does this make sense to everyone?
What does the x to the j mean? Or why are you saying x? The j to x?
Yeah, so, okay. So we have a bunch of different training examples, right? And each of those have multiple features, right? So for example, we could have two features, one which is like the temperature and one which is the overcast versus sunny. So I indicates like which feature we're talking about, and J is like just which example. So like, for example, in document classification, you'll have a whole bunch of documents. So J would be just like which document are we talking about, right? Because each feature has a different value in each document.
And so in, I don't know, the temperature case, we could have like different Fahrenheit degrees, right?
It would be like different days or something like that.
Okay.
Like let's say I gave you a whole bunch of examples of random days chosen from the past like 10 years. Then that would be our sort of training set. So each So j would sort of, each value of j would indicate a different day. And then I would be like which feature, temperature or overcastness. Yeah. That's all. Okay. Questions? Okay. And then, so how do we estimate pi? Do we do anything different from what we did before? No, we do the exact same thing because it's still a Bernoulli distribution, simple, the number of example. And when I say example, I mean like a training example. So like for the weather example, it would be like the number of days with label 1 divided by the total number of days. Or for document classification, it's the number of documents with label 1 divided by the total number of documents. Okay. Cool. So that's basically an overview of naive Bayes. Now I'm going to talk a little bit about the different ways to do naive Bayes for document classification. But if you have any questions about this stuff, think about them while I'm erasing some. Questions? Yeah. Yeah, so if you want to predict a continuous y, you'll do something maybe like linear regression, which we'll learn about next week. I don't think you can do naive Bayes for continuous variables. Yeah. I think naive Bayes is a classifier. Usually when you predict discrete variables, you would do classification, and when you predict continuous valued labels, it's regression. So you need like a model that's equipped for regression. What you can do with naive Bayes is predict multiple different labels. Like you could have 3 different labels, like maybe, or 4 labels. Like maybe you want to predict winter, spring, summer, or fall instead of just, winter or summer. And then you would do the same thing except for like y can take on 4 different values, right? But you could still calculate the probability of each value of y given the features, right? So you just calculate each of those 4 values, and then you would choose the one with the highest probability for a test example. Yeah?
From the previous one, we have calculated mu I cap, right? So we summed up the exercise over all the samples where the label was 1. So what exactly is summing up of xi represented? Is there a way to visualize that?
A way to visualize, so xi is like, so let's say it's the temperature. So let's say xi is the temperature.
And we have a label saying based on temperature we predict whether it's sunny or not or something like that.
Yeah, based on temperature, we predict whether it's winter or summer. Should be pretty easy to predict. You might get a few wrong if there's like a weirdly warm day, right? But it should be pretty easy. So to calculate the probability of xi given that y equals winter, right? All you do is you look at all the days that are labeled winter, right? You add up the temperature, and then you divide by the total number of winter days. So it's basically you look at the average winter temperature.
So it just added the temperature.
So it's just like the average, the mean, only among the days with a particular label for y.
What's the significance of I
I is which feature. So in this case, I just is an indicator for like the temperature feature. Like you could have 10 features. You could have temperature, you could have wind speed, you could have, you know, atmospheric pressure, you could have rainfall, you could have a whole bunch of features. And I is just like, and you might number them. Let's say feature number 1 is temperature, feature number 2 is wind speed, right?
So how does the summing up work then? So if we have two features, x1 and x2.
You just do it independently for each one, separately. You calculate the average temperature on winter days, the average wind speed on winter days, the average. So if you noticed, what I wrote was this. Okay, let me just rewrite it so that it's clear. So mu sub I, when I say sub I mean for a particular I, right? So you'd have, say you have 3 features. Then you'd have mu1, 0, mu2, 0, and mu3, 0. And you'd also have, over here, mu1, 1, mu1, 2, or sorry, mu2, like that, and mu, right? So this is like, so let's say 0 is winter, and 1 is summer. And then the first feature is, let's say it's temperature. So this is just the average temperature on summer days. This is the average temperature on winter days. This is the average wind, let's say feature 2 is wind speed. This is the average wind speed on winter days. And this is the average wind speed on summer days. That's it.
What's the significance of the constant variance for both the exercise that we were doing? X given y equal to 0 and x given y equal to 1. So assume that both have the same variance.
I just did that to make it a little simpler. You could also estimate the variance for each model, for each distribution. At which point, you can calculate the MLE for both the mean and variance. So in that case, you would have 2 parameters for each distribution. You'd have to calculate sigma squared 1, 1. And then you'd have sigma squared, 1, 2, etc. For the variance, I don't know it off the top of my head. I'd have to look it up. Yeah. I mean, I think it's pretty simple, but I don't want to make a mistake. Yeah.
It's kind of on the same lines as the sample.
Yeah. Okay? Okay. And actually, one more point of clarification, just so everyone is on the same page about the whole sort of training data, test data, et cetera. When you think of your data set, it's useful to think of it as like a big table, or maybe even 2 big tables. So let's say this is your training data. So basically you have a big table with x1, x2, x3, and y. I just used 3 features because I didn't want to write more, right? But you could have 100 features, you could have 1,000,000 features, whatever. And then, so your columns are your features and your label. And then your rows are your training examples, right? So here I'd have like different values, like 0, 1, 0, 1, 0, 0, 0, 0, etc. And it's all filled in. Okay? So just sort of each row is an example, a training example, and each column is like a feature, and maybe the last column is your label. And then in your test data, you can think of it in the same way. The only difference being that usually maybe you don't know why. Or you do, but you pretend you don't so that you can predict why and then calculate how well you did, right? So maybe it's something like that, right? And when I was using those I's and J's before, I was just using I to indicate like which column we're in and J to indicate which row we're in. Okay. So for document classification, there's sort of two commonly used models, right? The simpler one is the Bernoulli model, and then the slightly more sophisticated one is the multinomial model. So I'm just going to sort of briefly go over how you set each of those two models up to perform document classification. Okay. So let's imagine we have a bunch of documents. So each row in our table is a document, each column is a feature, and then we also have labels. In the binomial model, basically, what we do is we represent each document in the following way. So we have a big vector, and each position in the vector corresponds to a word in our vocabulary, right? So the first one could be like aardvark, and then the last one could be like zebra. And in total, we have this many v, that's the size of v is a set of all words, and we have the size of v is the size of our vector, right? So we might have a 0 if the word does not appear in the document. Maybe the second word does appear in the document. And finally, zebra also does appear in the document. So we just have an indicator variable for whether each word appears in the document or not. And that's how we represent each document mathematically. And then basically, all we're going to do is use the following model. So we again have to specify the same three distributions that we did in the previous two sort of examples. So here we have the distribution of y, which is going to be Bernoulli if you only have two document labels. The distribution of xi given y equals 0, which is again Bernoulli. And xi given y equals 1, which is again Bernoulli. So these distributions just represent the probability that the ith word in the vocabulary appears in your document, given your document has label 0. So let's say label 0 is that your document's about science, and label 1 is that your document is about, forgot what I said before, but what? History. I said history. So you can imagine that, let's say the word is, I don't know, cell, right? It might be more likely to appear in a document about biology than about history. And similarly, the word Renaissance might be more likely to appear in a document about history than about biology. So this is the exact same model, same type of model that we sort of worked through before, right? So you're going to calculate these p's for each word and for each label. And then you'll calculate pi, which is just the probability that a document is about biology, and the probability that and 1 minus pi is the probability that a document is about history, or something like that. Make sense? Okay. So now let's talk about the multinomial model. Actually, let's just use the other board. Okay. So this one is a bit more confusing. In fact, the way that each document is captured is a bit strange. But you'll see sort of how it makes sense once we work through it. So in this case, you're going to represent each document as, again, as a vector. But in this case, it's a vector where each element in this vector represents the word that appears in a particular position in the document. So let's say your document is let's say your document has these 5 words. Okay? So let's say that when you look up this in your dictionary, it's the 999th word. But it's the first word in your document. So in the first position of your vector, you're going to put something like 999, or some value to indicate that it's like this particular word. Okay? And then for the second sort of feature, you're going to write an indicator for the word document. So let's say it's like the 101st word in your dictionary. And then you're going to do sort of the same thing. Or something like that. So these numbers don't really matter. It's just, the only thing that matters is like, let's suppose later on, let's suppose your document's a little longer. When the word about appears again, you're going to use sort of the same label. So let's say this one is like 10, and this one's like 40 or something like that. So here I put 21 twice because I had the word about appeared twice, right? Okay, so we encode our document in this way. So let's not worry too much about this for 1 second, but just the point is that we now know about like each occurrence of each word, not just whether the word appeared or not. So we have sort of more information that we're encoding, right? Okay, and then this is the model that we're going to use. So again, we have y as Bernoulli. The only time the distribution of y will change from Bernoulli is if you have like multiple class labels, like if you're trying to predict multiple document topics. And then what we're going to have is xi given y equals 0 is going to be distributed according to a multinomial distribution with parameter theta 0. So what you notice about this parameter is that it's not dependent on I. So every word, or every sort of position is sampled, the word at every position is sampled from the same distribution. Okay, so and we have a second one for the distribution of the words given that y equals 1. So a multinomial distribution, basically, this theta 0 is of length. Theta 0 is a vector where you have one entry for each word in the vocabulary. So it's basically a vector of length v. So it's like theta 0, 1, theta 0, right? And same for theta 1. And each of these entries just represents the likelihood that you're going to choose this particular word given that y equals 0. Questions? So it seems a little strange at first because you're actually going to have feature vectors of different lengths for different documents, right? Because not all documents have the same number of words. So it's a little bit strange until you realize that sort of the distribution for each position is the same, right? So you still have like a fixed number of parameters to estimate. So theta 0, which is like v-dimensional, and theta 1, which is also v-dimensional. Okay?
So the position of the word comes into 0 now.
Say that again?
The position of the word in the document,
What about it?
in the end, it doesn't matter?
Exactly. In the end, it doesn't matter. It seems at first like it does, but because of the way we're parameterizing it, ultimately it doesn't matter. But what what sort of we are taking into account is like the number of times different words appear. So that's actually the information that we're adding in relative to the Bernoulli model.
And the multinomial distribution is the mean word that will come out in the distribution based on the words that make it up, I guess. What?
The multinomial distribution is sort of just like, think of it as like you have a likelihood for each category. Like, so you have a likelihood for each word, basically. So it's like, if you think of like how you might sort of generate this document given these probabilities, let's say you choose that first the document's going to have label 0, so it's going to be about biology or whatever. Then you start off and you're like, okay, I'm at position 1. Let me choose a word. So what you do is you go over to this multinomial distribution and you sample from this distribution, this first one, this probability of xi given y equals 0. And let's say like, so in this multinomial distribution, certain words will have higher probability than others, right? And so you'll be more likely to sample the word cell than the word renaissance in this, from this multinomial. So that's basically it. Okay? So I think we can stop recording and you guys can ask more questions if you have them.